Here we come to another part of climate change mitigation, and here I'll explain a different part of machine learning. But first, deforestation. Deforestation has been disastrous for our planet since we have found good profit for goods in forests like Amazon. Also, we know that trees act like a sink where all the world's carbon dioxide is absorbed. So it's logical that we try to decrease deforestation as much as possible. But for this, we need some strategy to plan our policies. This planning will require us to know where and how much deforestation is occurring, and machine learning can play its role in this. This is not a prediction problem unlike what we have discussed before. This is a problem of computer vision. From part 2 of this series, we already know how useful convolutional neural networks are, and this is one of their best uses. For example, we could take a satellite image of a part of a forest now. Then we pass it through a CNN module which labels what each parts are. Like we have a river and a cloud here. Rest all is just forest. Now after a year we take another image of the same place. We see it's changed a lot. We have a mine and an agricultural village here. So you can see if you automate this labeling part, then we can continuously track deforestation in places around the world. Here we face another problem. If you look at the resolution of the two of the most used satellite techniques, we see that the resolutions are 30 meters per pixel and 250 meters per pixel. This means that an area of 30 meters by 30 meters is embedded in 1 pixel, and with an image of that many pixels, you can estimate how coarse the image will be. Because of such low resolutions, we need to increase our capabilities. Now, rather than trying to develop new neural networks for this, we can increase the accuracy of already present networks. For CNNs, we can use pre-processing the data, or we could change the hyperparameters of the model, or we could use a core concept and find different ways to implement it. Lastly, we could use ensemble methods as well. Pre-processing our data is basically done when we cannot increase the quantity of the data, so we try to increase the quality of the data. Maybe some of the data is inaccurate or missing, so we could modify the outliers and treat the missing values to increase the quality of the data. We could also use our knowledge to help the model. For example, we know that clouds are mostly white, so rather than training the model to learn that clouds are white, we could just say that if there are a bunch of white pixels together, then it's a cloud. Like this, we could make a better model and a much more accurate one. Hyperparameter tuning will not cause that big of a difference if our model is made properly. Hyperparameters are basically instructions given to the model to guide its training. Like the number of times it trains is called the number of epochs. But know that larger epochs don't actually mean more accuracy because of something known as overfitting. Search it up to get more information. Another instruction we give is how the model finds how wrong it is. It is called a loss function. Like in our linear regression model in part 2, we use distance for our loss. Here, distance won't be applicable at all, so we use a different loss function. Lastly, we have the optimizer. Optimizer is the last part of our generic algorithm for machine learning that we were discussing. After finding the loss or how wrong a model is, what process should it follow to tune itself to be more accurate? That is the job for optimizer. Now the following part will have the greatest impact on the accuracy. We know how a generic CNN works, but using the same core concepts, we can develop two other networks, the ResNet and the InceptionNet. These networks add more functionality to the already present convolutions. As you can see, ResNet basically uses many layers, but from experimentation, we know that more layers don't actually mean better, it's actually worse. So the ResNet skips connections to avoid that problem. You should research that, it's really interesting. We also have the inception net, which is basically a branch CNN. But you can see how we take the core concepts and apply them in different ways to achieve more accuracy. Lastly, ensemble methods are basically combining different models into one prediction, and we can see how different CNN models are and how different their accuracies are. The simple CNN model only has a score of 0.75, but other variations reach up to 0.89. So we can have a great increase in accuracy by having a different perspective on our models. Rather than wasting more money on better satellites, we can make our models more efficient, saving money and time while doing so.